Hey, what's up, Chem Peeps? Who is ready to determine your potential? You have so much of it. You have so much potential. For each of the net ionic equations described below, determine the standard potential, E naught, for the overall reaction as written. Then, use the value of the cell potential for the overall reaction to determine whether or not the reaction is spontaneous, thermodynamically favorable, as written. Let's take a look at this first one. I'm going to quickly assign some oxidation states. Easy enough because they're either neutral atoms or monatomic ions. Let's take a look at copper. Goes from the 0 to +2 oxidation state, indicating that it's been oxidized. Boom. Oxidation half reaction. Scope out silver. Goes from the +1 to 0 oxidation state, indicating it's been reduced. Boom. Reduction half reaction. Anytime you're not provided reduction potentials, just go to your friendly reduction potential chart. Find me some copper 2, find me some silver. Now, recall that as written, our copper is undergoing oxidation. So its oxidation potential is going to be the same numerically, but opposite in sign as what we find on the reduction potential chart. Therefore, oxidation potential negative 0.34 volts. Silver, because it's being reduced, we're just gonna pull the exact value directly from the reduction potential chart. Reduction potential positive 0.80 volts. If I were to sum these equations together, electrons lost equals electrons gained. Notice that we get the original overall equation again, and the cell potential for the overall reaction is just a sum of the oxidation and reduction potentials, which in this case would be positive 0.46 volts. Boom. Now, as you think about what this cell potential tells me that as written, this equation is thermodynamically favorable. Boom. It will happen without any outside source of energy. Let's do another example. Assign some oxidation states. Again, easy enough because all we're doing are elements and monatomic ions. Start with zinc. We go from the 0 to +2 oxidation state, indicating that it's lost electrons being oxidized. I'm going to write out the oxidation half reaction. Boom. Now, if you're wondering why I came up with 6 electrons here, note that each zinc goes from the 0 to +2 oxidation state, and I've got 3 of them, which is why I'm losing 6 electrons total. This equation has already been balanced for charge, something we'll talk about in a little bit. Let's look at aluminum. Aluminum's going from the +3 oxidation state to the 0 oxidation state, indicating its gained electrons been reduced. Boom. All right, let's come up with some oxidation and reduction potentials. This time we're looking for zinc and aluminum. Zinc is being oxidized, so its oxidation potential is going to be the same value but opposite sign, positive 0.76 volts. Aluminum, because it's being reduced, and this is a reduction potential chart, we're just gonna pull that potential directly off that chart. Boom. Negative 1.66 volts. When we sum electrons lost, electrons gained, we end up with the overall equation, and to determine the cell potential of the overall equation, we just sum these two together. We get negative 0.90 volts. I'm going to time this out. Don't forget to keep in mind your significant figures and your rules for addition and subtraction with significant figures when you're adding these potentials together. Boom. What does this cell potential tell me? It's negative, indicating that as written, this is thermodynamically unfavorable. In other words, this reaction is not going to happen spontaneously. If we wanted this to happen, we would have to put some energy in order to force zinc to give up those electrons. We are done.